As you have just seen, there's nothing too difficult about the propositional representation. So we can now turn to the data structure that is maintained by the graph plan algorithm, and that is the so-called planning graph. I will first describe a basic version of this data structure, which does not contain mutex relations. I will define those later, as you can see here. To understand the properties that the planning graph represents, I want to remind you of a proposition we have seen earlier, and that was about solution existence to planning problems. And this was the proposition I want to remind you of. So if we are given a planning problem consisting of a state transition system, an initial state, and a goal, we can say that this planning problem has a solution if and only if the following condition holds. And the condition is that the set of all possible goal states intersected with this set here must not be empty. And this set really represents all the states that are reachable from the initial state. We also had a similar proposition for the regression of states, but that's not what I wanted to remind you of here. It's the first proposition that I want to have a closer look at. This states that if a planning problem has a solution, then there must be a reachable goal state. Now, our goal condition G actually consists of a set of sub-goals that we're trying to achieve. Let's call them G1 through Gn here. Now, a corollary of our original proposition is that each of these individual sub-goals must be true in some reachable state. It is, of course, trivially true because they will all be true in the reachable goal state. But I can also turn this around now. Now, suppose I could show that there is one goal condition in here that cannot be achieved. So one of the goal conditions is not reachable. If I can show that one of the goal conditions isn't reachable, then that means there can be no state in which this goal condition is true, which means there can be no state that constitutes a solution. So the planning problem does not have a solution. And that is exactly the kind of insight that the planning graph will give us. Of course, what we have done in our forward tree search algorithm is constructed effectively a reachability tree. In this tree, our root node was the initial state Si that was given as part of the problem. And for each node S, we had the children of a node S be gamma of S. So that's the immediate successors of that state S in this set here. And then we had the arcs labeled with the actions that correspond to the state transitions. That is the tree we constructed in forward search. Now, in this tree, if we constructed the complete tree, are all the nodes that are reachable from our initial state. So this is a complete reachability tree for our planning problem. Or if we gave a depth limit to our tree, so suppose we only go to depth D, then we would have gamma D of Si in this reachability tree. So not a complete tree, but all the nodes that are reachable in D steps. And in this tree, of course, we can find all the solutions to problems that require up to D actions in their solution. Now, we could of course use this tree to check whether each of the individual goal conditions is true in some state rather than all in the same, and then use our criterion just introduced to see whether the planning problem has a solution. But that is of course not an efficient way of solving planning problems, as we know that even a tree of depth D has an exponential number of nodes in it. Here, k is the number of applicable actions per state, and d is the depth, so we have k to the d nodes in general in such a tree. But there is a more clever solution to this reachability question, as we will see next. I will now describe to you the planning graph, which is the fundamental data structure maintained by the graph plan algorithm. And I will start by describing what nodes are contained in this graph. So the planning graph is a layered directed graph, G, consisting of nodes and edges. And that means the edges are directed so they go from one node to another, only unidirectional. And the graph is layered, which means the nodes in the graph can be divided into disjoint sets. And each of these sets is called a layer. So if we look at the nodes n contained in the graph, they consist of the layers P0, A1, P1, A2, and so on. These are our layers in the graph containing the nodes. And we distinguish two types of layers we have in our graph. Firstly, there are the state proposition layers denoted by symbols with a P, P0, P1, etc. And then we have the action layers denoted by the symbol A, A1, A2, etc. And these types of layers alternate in the graph. So we start off with a proposition layer, P0, followed by an action layer, followed by a proposition layer, followed by an action layer, followed by a proposition layer, etc. So they alternate in the graph, and the first layer, P0, is a proposition layer. So let's have a look at the nodes we find in the first proposition layer, P0. In the first proposition layer, we have a node for each proposition that was true in the initial state. So Si, our initial state, is a set of proposition symbols, and in P0 we have a node for each of these proposition symbols. And given this definition of P0, we can now define what nodes we find in the action layer Aj. So that's not just the action layer A1, but in general the action layer Aj, which follows the proposition layer Pj-1. And effectively, we have in this action layer all the action symbols that represent actions that would be applicable in the preceding proposition layer. So what we do is we look at our preceding proposition layer Pj-1 and we interpret this as a state. Remember, the nodes in this layer will be proposition symbols, so we can simply form a set of all these nodes and interpret this as a state. Usually this won't be a meaningful state, as it may contain symbols that can never be true at the same time. For example, that the robot R is at location 1 and that the robot R is at location 2. But never mind that now. So we interpret this proposition layer as a state and then add to the successive action layer all those actions whose preconditions are satisfied in that state. Now we know what P0 contains and what the jth action layer contains. We can now define the proposition layer Pj, where j of course has to be greater than 0 because we've already defined P0. And in Pj, we find nodes for all those proposition symbols that were already in Pj-1. So all the propositions that were in the previous proposition layer are also in this proposition layer. But there may also be additional nodes that were not in the previous proposition layers. And what we do to find these nodes is we take all the positive effects of all the actions in the preceding action layer. So Aj is the preceding action layer. We take all those actions and we look at their positive effects and we add a proposition node for each proposition that is a positive effect to layer Pj. So in Pj, we have all the propositions from the previous proposition layer plus all the positive effects from the previous action layer. Note that we ignore the negative effects of the action here, so we only look at the positive effects. We do not remove the negative effects from any layer ever. An interesting observation here is that the layers must be monotonically increasing from proposition layer to proposition layer and from action layer to action layer. So for proposition layers, this is quite easy to see. We always take over the propositions from one layer to the next and possibly add new propositions to that next proposition layer. So it must be monotonically increasing. The action layers must also be monotonically increasing, because if an action is applicable in one action layer, then it must also be applicable in the next action layer, because all the preconditions that were true here must be true in the next proposition layer, so they must still be true for the next action layer. So proposition layers and action layers are monotonically increasing. So now that we have seen the nodes that exist in the planning graph, we can look at the edges between nodes, or because it's a directed graph, I like to call them arcs. So the first set of arcs we have all go from proposition layer Pj to action layer Aj, that is the action layer that follows it. And they go from a node in this layer, which is a proposition, to an action in the following layer, if the proposition P is a precondition of that action. Similarly, we have arcs from the action layer Aj to the proposition layer Pj, that's the proposition layer that follows the action layer. And we have an arc from an action A in this layer to a proposition P in the following layer, if either P is a positive effect of that action, or P is a negative effect of that action. In other words, each action in an action layer Aj is connected to its preconditions and its effects, and it's connected to the preconditions in the preceding proposition layer and to its effects in the following proposition layer. And these are all the arcs that exist between different layers. So there are no arcs between other layers. Arcs only go from one proposition layer to the following action layer, and from one action layer to the following proposition layer. They don't go between other layers. Now, I should mention that these edges aren't all the edges that exist in the planning graph. There are other edges, but these edges are strictly internal to the layers, and we will look at them later.